Really, this is quite an old idea. I'm referring to the work of Seymour Papert, Powerful Ideas for Thinking. And this is sort of my lens for understanding programming as a mathematical activity, or mathematics as a programming activity, which way you think about it. Thanks, John. Can anybody tell me what this piece of code does? Prediction, what's this do? Just yell it out. It's a square, okay. This was produced by a 4-year-old in his very first session programming. So we sat him down and we showed them what the different blocks did. And then we said, go to work, what do you want to make? And this child decided to make this program. He doesn't use the repeat command, he's not using any conditionals. He can't read yet, so he's able to program before he can read. This is another example of a program from a child. They have an unnecessary pen down statement twice in their code. They're playing with the code, trying to figure out what it does. They're learning about powerful ideas in mathematics through the activity of coding. They're learning mathematics from the coding activity as an alternative to perhaps doing coding as an assessment. Did you learn the mathematics? I'm going to just demo what I started this out with the kids. I thought it was really important the kids learn how to think with their body first, so the debugging would be a lot easier. John's going to be the programmer, and I'm going to be the computer. He's going to be able to give me either a turn right command or a move forward command. And his objective is to make me draw something on the stage that's obvious enough that you guys know what he's trying to make me draw. Warning, he doesn't know how far I turn right yet.
You know as much as I do at this point. Okay, go forward. Okay, turn right. Go forward. Turn right. This seems easy. Go forward. Turn right. Go forward. So I guess that's my first shape.
What shape did I make? Rectangle. No, not yet. Close. I haven't finished the last side yet, have I?
We started with a forward. Turn right.
No, but I started here.
I see. It's an observation test as well.
Okay. So the point was that there was not to try to make John look foolish. The point there was to show that thinking with our bodies as part of programming is really important. And a lot of people who program visualize the code in their head when they're trying to do it. And with kindergartners who are really used to using their bodies, that's a great place to start. This is another example of a program. Again, all three of these are from examples of one 40-minute session, which was all I could manage to, unfortunately, squeeze into the kindergarten curriculum. But here's kids learning sort of some mathematical ideas that are, I think, interesting and sort of age-appropriate. This is my son. So he sort of sat down and said, what's this arc thing do, and what's this turn right thing do? And he's learning about symmetry and how to produce symmetry from his mathematical commands that he's using. And then this is a student who doesn't actually have a program at all. What she has is 3 commands she's pulled out, and she just reuses them over and over again to produce this shape that she's trying to build. This is sort of in progress, and I think we can all see where it's going to try to go. So clearly she's using some symmetry, some ideas in symmetry, as well as ideas around procedures to build this program that she's got. This is just mathematical art. I find kids are kind of motivated by making the computer make fun-looking things. This is my first in-school programming environment. It was a TI-83, which is a pretty terrible programming environment, I might add. And this is a kid who is sort of like learning about conditionals and learning about logic, learning about telling the computer to do one thing in this case and one thing in this other case, which is a really, I think, an important idea in mathematical reasoning. This is not from my class. This is from a class of a teacher. I don't actually know where she lives. She just sort of sent it to me through the internet. Her name's Amy. And this is Evan, who lives in China. And so he was doing a unit on lines. And so then the idea when the unit, so this is him sort of assessing what do the kids understand of lines. So the kids are building some mathematical art using what they understand of lines to sort of translate that into code. And I think maybe they were a little motivated by it. And this is an example of a discovery which I don't think is a groundbreaking discovery necessarily, but this is like my own mathematical learning. I saw someone created this random walk, and I thought that's fascinating. And I wonder what it would look like if I drew pi, and what would it look like if I drew root 2 and all these sort of other irrational numbers. So I drew these numbers in the code, and then I asked myself, what does a rational number look like if I draw it in the code? It turns out very different. Rational numbers are very visibly different than irrational numbers when you draw them using the sort of random walk. The idea in this random walk is the same turning that I was doing, but each digit represents a portion of the turn that I was making, and they always move the same distance. And then realizing later this is probably unbounded, even though it doesn't look like it. So were I to continue this for literally forever, pi is going to cover the plane, which I think is interesting. Anyway, that's just some examples that I'm sharing, and here's some contact information.
Thank you very much, David.
Yeah.